The architectural layout of an operating system defines how its functional components are arranged and how they interact. In a monolithic kernel, every core service, process scheduler, memory manager, file system, networking stack, device drivers, etc., resides in a single address space and is linked together at build time. This design resembles a large open-plan kitchen where all appliances share the same countertop. The CPU can call any routine directly with a simple function call, which yields low latency and high throughput. However, because the whole kitchen is one continuous space, a defect in any appliance, for example, a buggy network driver, can corrupt the entire environment. In a microkernel architecture, the kernel is intentionally kept minimal, typically only the scheduler, IPC dispatcher, and low-level hardware abstraction, timer, interrupt handling, and basic memory protection. All other services, file system, networking, device drivers, GUI, etc., run in separate user mode processes and communicate with the kernel via message passing. This model is akin to keeping only a stove in a tiny pantry. Every other appliance lives in its own room and must request the pantry to perform critical actions. The advantage is fault isolation and a drastically reduced trusted computing base, because any bug in a user mode server cannot directly corrupt kernel memory. The trade-off is additional context switches and IPC latency for each cross-component request. Practically, this architectural decision influences boot time. Monolithic kernels can boot faster because services are pre-linked. Microkernels need to launch many user mode servers after the minimal kernel boots. Maintainability. Updating a driver in a microkernel does not require rebuilding the kernel image, whereas monolithic kernels often need a full rebuild and reboot. Security. The smaller the code residing in privileged mode, the lower the attack surface. Microkernels therefore lend themselves to formal verification. The choice between the two models is a classic engineering trade-off between performance, monolithic, and robustness, extensibility, microkernel. Kernel size is measured in lines of code, LOC, and binary size, kilobytes or megabytes. A monolithic kernel typically aggregates hundreds of thousands of LOC, translating into a binary that may occupy 5 to 20 megabytes of RAM on boot, depending on the configuration and included drivers. Because the kernel runs in a single address space, all of its subsystems, file system, network stack, device drivers, and so on must be resident in physical memory simultaneously, even if many are idle. A microkernel, by contrast, can be reduced to a few thousand LOC, often less than 50 kilobytes, and a binary size of a few hundred kilobytes. The microkernel itself performs only scheduling, IPC routing, and low-level hardware abstraction. All additional services are loaded as separate processes that can be paged in and out based on demand. This leads to a lower static memory footprint and a more flexible runtime memory allocation. Resource utilization model. Let M sub k equals memory used by the kernel binary itself. M sub d equals cumulative memory of device drivers and core services. M sub u equals user space memory. Total M equals M sub k plus M sub d plus M sub u. Total M equals M sub k plus sigma I M sub service I plus M sub u. Because M sub k in a microkernel is dramatically smaller, the system can allocate a larger proportion of RAM to user applications, M sub u, without sacrificing stability. In embedded or mobile contexts where RAM is limited, for example 256 megabytes, this distinction can be decisive. CPU utilization. The microkernel's small codebase also reduces instruction cache pressure. Fewer kernel instructions mean higher instruction cache hit rates, leading to lower CPU cycles per system call. However, the extra context switches and message copies needed for service interaction can increase overall CPU usage for certain workloads, which is why workload profiling is essential when choosing an architecture. IPC is the conduit through which isolated processes exchange data. In a monolithic operating system, processes typically share the same address space or can map shared memory directly, allowing a direct memory copy or even a zero-copy transfer. The overhead is essentially the time to copy the payload T copy, plus the minor cost of acquiring a lock, if any. In a microkernel, every IPC request must traverse the kernel as a privileged mediator. The typical sequence is Copy in, the sender places the message into a kernel-owned buffer T copy in. Lock acquisition, the buffer is locked to prevent concurrent modification T lock. Kernel routing, the kernel validates the destination, queues the message, and possibly triggers a context switch T kernel. Unlock, the buffer lock is released T unlock. Copy out, the receiver copies the payload from the kernel buffer to its own address space T copy out. The total IPC latency can be expressed as IPC time equals T copy in plus T lock plus T kernel plus T unlock plus T copy out. If we assume symmetrical copy costs, T copy in approximately equals T copy out equals T copy, the formula simplifies to IPC time equals 2 times T copy plus T lock plus T kernel plus T unlock. Typical measured values on a modern ARM Cortex of 53 at 1 GHz might be T copy approximately 0.3 microseconds per 4 kilobyte payload. T lock approximately 0.05 microseconds. T kernel including a context switch approximately 1.2 microseconds. T unlock approximately 0.05 microseconds, resulting in an IPC latency of roughly 2.1 microseconds for a 4 kilobyte message, compared to 0.4 microseconds in a monolithic system. While the microkernel adds overhead, it gains security guarantees. Each message is validated, and no process can directly corrupt another's memory. In high-throughput scenarios, such as network packet forwarding, microkernels mitigate this cost by using zero-copy techniques such as shared memory regions that are transferred by capability rather than by copy, reducing T-copy to near zero. Therefore, when designing a system around a microkernel, architects must weigh the added latency against the benefits of strong isolation and the possibility of optimizing IPC paths for critical services. A system call is the controlled entry point from user mode into privileged kernel mode. The latency of a system call consists of 3 primary phases. Entry, the CPU saves the user mode register context, switches to kernel mode by changing the privilege level in the CPU's status register, and jumps to the system call handler stub. This involves writing registers to the kernel stack and possibly flushing the translation look-aside buffer for address space changes. Service, the kernel executes the requested operation. In a monolithic kernel, the needed code, for example file system driver, is already resident, so T-service is mostly the execution time of the operation itself. In a microkernel, the service may be delegated to a user mode server, so T-service includes additional inter-process communication messages and possibly a secondary context switch. Exit, the kernel restores the saved user mode registers, switches back to user mode, and returns control to the application. The overall latency can be written as latency equals T entry plus T service plus T exit. Quantitative example, x86-64 3 GHz. T entry approximately 30 nanoseconds, saving about 16 registers, updating CR3 for page tables. T exit approximately 30 nanoseconds, restoring registers, returning via sysret. Monolithic T service for a simple getBID call approximately 50 nanoseconds. Kernel reads a per process data structure. Microkernel T service for the same logical request. Inter-process communication to PID server 1 microsecond, including context switch. Server processing 40 nanoseconds. Inter-process communication reply 1 microsecond. Total T service approximately 2.08 microseconds. Thus the total latency becomes monolithic 30 nanoseconds plus 50 nanoseconds plus 30 nanoseconds, approximately 110 nanoseconds. Microkernel 30 nanoseconds plus 2.08 microseconds plus 30 nanoseconds, approximately 2.14 microseconds. The microkernel penalty is roughly 20-fold for this trivial call. However, for complex operations, for example file input-output, the monolithic kernel also incurs significant internal processing, narrowing the gap. Moreover, modern microkernels can batch multiple inter-process communications or employ fast path optimizations. For example, shared memory remote procedure call to bring T-service down to sub-microsecond levels. When modeling system performance, architects often use a Markov chain or queuing model where the service time includes both CPU execution and the probability of a context switch. The model helps predict how many concurrent system calls a system can sustain before CPU saturation, guiding decisions on whether the microkernel overhead is acceptable for a given workload. Fault isolation is the capability of a system to contain the impact of a failure to a limited region, preventing a cascade that crashes the entire operating system. In a monolithic kernel, all kernel components share the same address space. If a buggy device driver dereferences a null pointer or writes to an invalid memory region, the processor typically generates a fault that propagates to the kernel, resulting in a kernel panic and a full system reboot. The entire system becomes unavailable until manual intervention. A microkernel enforces isolation by executing each server, driver, file system, network stack in its own user mode process protected by the hardware memory management unit. A fault within a server triggers a user mode exception that terminates only that process. The microkernel can then detect the failure via a watchdog or by monitoring the interprocess communication channel for abrupt termination. Log diagnostic information such as register state and backtrace for post-mortem analysis. Restart the failed server automatically, optionally reinitializing hardware resources, and notify dependent services through a predefined recovery protocol. Consider a network driver that crashes while processing a malformed packet. In a microkernel system, the driver process receives a segmentation fault, terminates, and the microkernel captures the exit status. A network manager service receives a driver down event, releases the network interface card DMA buffers, and spawns a fresh instance of the driver binary. The network interface card is reinitialized without requiring a reboot. Existing user applications such as browsers and Secure Shell continue to run, possibly experiencing a brief temporary loss of connectivity. In contrast, the same crash in a monolithic kernel would bring down the entire operating system, forcing all applications to restart. Stability metrics include mean time to failure, which is typically higher for microkernel systems because isolated components can be swapped without affecting the rest, and mean time to recovery, which is lower for microkernels due to automated restart mechanisms. Recovery can be measured in seconds rather than minutes for a full reboot. Overall, the microkernel approach dramatically reduces downtime and improves service-level agreement adherence, especially in mission-critical embedded or aerospace environments where rebooting is prohibitive. The Trusted Computing Base, abbreviated TCB, comprises every component whose correctness is essential for the overall security of the system. Any vulnerability inside the TCB can be leveraged to breach the entire platform. In a monolithic design, the TCB includes the entire kernel binary, scheduler, memory manager, file system, networking stack, and all device drivers. For a typical Linux kernel, this can be on the order of 5 to 10 megabytes of code and greater than 200,000 lines of code. The large TCB size complicates formal verification, static analysis, and thorough testing. Historical vulnerabilities, for example Spectre and Meltdown, often arise from complex interactions between subsystems inside this vast TCB. A microkernel reduces the TCB to the minimal set of primitives required for safe operation: interprocess communication dispatcher, thread scheduler, and low-level hardware abstractions such as timer, interrupt controller, and basic memory protection. The binary size can be as small as 50 kilobytes and less than 5,000 lines of code. This dramatically improves the feasibility of formal methods such as model checking and interactive theorem proving. Projects like SEL4 have demonstrated mathematically proven absence of certain classes of bugs, for example memory safety violations, within the microkernel TCB. Capability enforcement. Microkernels often use a capability-based security model where each server receives only the rights it needs to function. This minimizes the attack surface. Least privilege execution. Even privileged services, for example a network stack, execute in user mode, limiting the privilege escalation potential of a compromised component. Isolation guarantees. The hardware MMU enforces that one server cannot read or write the memory of another, a guarantee that monolithic kernels rely on discretionary access controls and can be bypassed if a bug compromises kernel memory. Assume a vulnerability discovery rate of 0.1 bugs per 10,000 lines of code for well-reviewed code. For a 200,000 lines of code monolithic kernel, expected vulnerabilities approximately 2 bugs. For a 5,000 lines of code microkernel TCB, expected vulnerabilities approximately 0.05 bugs. That is a 95% reduction in the probability of a critical security flaw residing in the TCB. Consequently, microkernels are attractive for high-assurance domains, such as avionics, medical devices, and secure smartphones, where security guarantees must be provable rather than merely assumed. Extensibility describes how easily new functionality can be added without disturbing existing code. Modularity is the design principle that separates concerns into self-contained units with well-defined interfaces. In operating systems, these concepts manifest differently across architectures. Monolithic extensibility, adding a new device driver to a monolithic kernel, typically involves writing the driver code following kernel APIs, modifying the kernel build configuration to link the driver object file, rebuilding the entire kernel image, rebooting the system to load the new kernel. This is analogous to rebuilding the whole house to add a new window. The process is error-prone because any change can affect the entire binary, and a faulty driver may prevent the kernel from booting. Microkernel extensibility in a microkernel. Services are user mode servers that communicate via IPC to add a new capability. For example, a new file system, the developer implements the service as a standalone executable adhering to the kernel's IPC protocol, deploys the binary to the target system, often simply copying a file, starts the service, possibly registering it with a service manager. No kernel recompilation or reboot is required. The core kernel remains untouched, and the new service runs in its own address space, isolated from other servers. Runtime component loading microkernels can also hot swap components. Dynamic update. Replace a running server with an updated version while preserving state through serialization and deserialization. On-demand loading. Load rarely used services only when needed, conserving memory. Practical example, adding a new network protocol monolithic. Modify the network stack source, recompile the kernel, and reboot. Any regression may break all networking. Microkernel. Implement the new protocol as a user mode server, register it with the network manager, and start it. Existing applications continue to use the old stack. The new protocol is available instantly. Benefits: reduced downtime, services can be updated without system-wide reboots. Better fault containment, a buggy update affects only its own process. Simplified testing, each module can be unit tested in isolation. Thus, microkernel architectures provide a superior platform for continuous integration and deployment pipelines, especially in embedded or IoT devices where field upgrades are common. Performance evaluation of operating system kernels involves two complementary dimensions. Micro benchmarks, synthetic tests that stress individual subsystems. For example, context switch latency, IPC throughput, system call latency. Macro benchmarks / real-world workloads. Applications such as web servers NGINX, databases POSTGRESQL, or mobile app suites that reflect typical user behavior. Context switch latency. Monolithic kernel 70 nanoseconds to 120 nanoseconds. Optimized assembly. Microkernel 1.0 microseconds to 2.5 microseconds. Includes IPC. IPC throughput messages per second, 4 kilobyte payload. Monolithic kernel 5 to 10 million messages per second, shared memory. Microkernel 1 to 2 million messages per second, copy in out. File system syscalls stat open. Monolithic kernel 150 nanoseconds to 300 nanoseconds. Microkernel 1.5 microseconds to 3 microseconds. CPU-bound workload matrix multiply. Monolithic kernel 10% faster due to fewer hops. Microkernel approximately 5% slower. Energy consumption idle plus workload. Monolithic kernel slightly higher due to larger kernel footprint. Microkernel 5 to 10% lower, more cores can sleep. Web server NGINX. Under a 100,000 concurrent connection load, a monolithic kernel achieved 1.2 million requests per second with average latency 15 milliseconds. A microkernel version achieved 1.1 million requests per second with latency 18 milliseconds. The gap narrowed when enabling zero-copy sendfile via shared memory (IPC), bringing the microkernel within 2% of the monolithic figure. Database POSTGRESQL transaction throughput dropped by approximately 8% on the microkernel due to additional IPC between the storage server and the query executor. However, the microkernel exhibited zero downtime failover. When the storage server crashed, the kernel automatically restarted it, and active connections continued after a brief reconnection, whereas the monolithic kernel required a full database restart. Mobile phone Android battery life improved by approximately 7% on a microkernel-based variant because background services could be individually suspended, and the tiny kernel allowed deeper CPU idle states. Raw speed versus reliability. For compute-intensive HPC clusters where every microsecond counts, monolithic kernels remain the default. The overhead of message passing can become a bottleneck in latency-sensitive scientific simulations. Energy and uptime critical systems. Embedded, automotive, and mobile platforms benefit from the microkernel's ability to shut down unused services and recover from faults without reboot, often outweighing the modest performance penalty. Scalability. As core counts rise greater than 64 cores, the cost of a large monolithic kernel's contention on shared data structures, for example global locks, can increase. Microkernels with isolated servers can distribute load more evenly across cores, mitigating contention. In summary, the decision hinges on the primary quality attribute of the target system. When absolute throughput is paramount, a monolithic design wins. When safety, modularity, and energy efficiency dominate, the microkernel's modest overhead is an acceptable trade-off.